Automatic gear changes may be overridden by use of the 2 and 1 selector positions. If 1 is selected from rest, first gear will be held until the selector is moved to 2, when second gear will engage. Moving to D will then give third gear, provided that road speed and throttle opening are suitable. Selector position 2 also permits automatic changes, but from first to second and from second to first only, depending on road speed and throttle opening. Third gear will not engage in this position. With the vehicle cruising in third, selecting 2 will cause an immediate downshift to second. Selecting 1 in similar conditions causes an immediate downshift to second, and then, when road speed drops sufficiently, to first. Full engine braking is available in both second and first gears. This also applies when the vehicle is in reverse. The Planetary Gear Set is a Ravigno type with primary and secondary sun gears, primary and secondary planet pinions, and 1 ring gear. The ring gear is attached to the output shaft. The planet carrier is mounted in the transmission case on a one-way clutch. Both sets of pinions are in the planet carrier. They mesh in pairs. The longer outer secondary pinions mesh with the ring gear at their outer edge. At their inner edge, they mesh with the secondary sun gear. The smaller primary pinions mesh with the smaller primary sun gear. The planet pinions transmit the drive from the sun gears to the ring gear. In all forward ratios, drive is transmitted through the primary sun gear. In reverse, it is transmitted through the secondary sun gear. Control of the Planetary Gear Set comes from the operation of 2 multi-plate clutches, the one-way clutch and 2 brake bands. The outer plates of the front clutch are splined to the input shaft from the converter turbine. The inner plates are splined to the primary sun gear shaft. The inner plates of the rear clutch are splined to the front clutch drum. The outer plates connect to the secondary sun gear. The front band wraps around the outside of the rear clutch drum. The rear band is on the outside of the planet carrier to hold the planet carrier stationary when it is applied. When the rear band is in the release position, the one-way clutch lets the planet carrier rotate forward, but not in a reverse direction. These are the components and control elements engaged in each gear range. The front clutch, the rear clutch, the front band, the rear band, and the one-way clutch. The front clutch combines with other elements to provide the required ratios for all forward gears. When D is selected, the front clutch is engaged. The one-way clutch acts as the reaction member, holding the planet carrier stationary and stopping it rotating in the opposite direction to the input shaft. Power flow is from the input shaft through the applied front clutch to the primary sun gear, which turns clockwise. Since the primary sun gear is meshed with the primary pinions, the pinions rotate anti-clockwise. This turns the secondary pinions clockwise on their pins on the locked planet carrier. The secondary pinions turn the ring gear and the output shaft in a clockwise direction at a reduced ratio and with increased torque. The gear reduction in first gear is 2.39 to 1. The secondary sun gear rotates freely in the opposite direction to the primary sun gear. On overrun, when torque is applied from the road wheels, the one-way clutch unlocks and allows the planet carrier to rotate. The transmission-free wheels and no engine braking is provided. In selector position D and also in position 2, the front clutch and the front band are applied to obtain second gear. When the transmission changes from first to second, the front clutch remains engaged and the front band is applied to lock the secondary sun gear to the case. The secondary sun gear now becomes the reaction member. Power flow is from the input shaft through the applied front clutch to the primary sun gear and to the primary pinions. The anti-clockwise rotation of the primary pinions turns the secondary pinions clockwise. Since they mesh with the secondary sun gear and the ring gear, they walk around the stationary sun gear and rotate the ring gear in a clockwise direction. In both drive and overrun conditions, torque reaction is taken by the applied front band, which holds in either direction. The gear reduction in second gear is 1.45 to 1. In selector position D, the front and rear clutches are applied to obtain third gear. When the transmission changes from second to third, the front clutch remains engaged. The front band is disengaged and the rear clutch is applied. Since both clutches are now applied, the input shaft is locked to the primary sun gear through the front clutch and to the secondary sun gear through the rear clutch. With both sun gears locked together and to the input shaft, there is no relative motion between the gears. The whole gear set rotates as one unit to give a direct drive with a ratio of 1 to 1. In selector position 1, the front clutch and the rear band are applied. Application of the rear band locks the planet carrier to the case. Power flow through the gear set in the drive condition is the same as in selector position D, first gear. Drive is transmitted through the front clutch to the primary sun gear and through the short and long pinions to the ring gear at the ratio of 2.39 to 1. However, on overrun, the locked planet carrier acts as a reaction member, so full engine braking is provided. In reverse, the rear clutch and the rear band are applied. The rear clutch locks the input shaft to the secondary sun gear. The rear band locks the planet carrier to the case to provide the reaction member. The input shaft turns the secondary sun gear clockwise. The secondary pinions turn anti-clockwise on their pins on the locked planet carrier. The ring gear and output shaft turn in the reverse direction with a ratio of 2.09 to 1. Full engine braking is provided on overrun. Servos in automatic transmissions convert hydraulic pressure acting on a piston into a mechanical force. In this transmission, a front and a rear brake band are used. A servo is required for each. The rear servo is a pressure apply spring release type. Its piston has a central stem which locates in one end of the rocker arm to transfer the apply force to the band. A lever-type spiral spring returns the servo and band to the off position when the fluid is dumped. The rear band holds the planet carrier stationary when it is engaged. It is applied in drive ranges with low ratios. The high apply force required is provided by a combination of the large diameter piston and the leverage provided by the rocker arm. Fluid at line pressure is converted to an apply force by the piston, and this acts on the longer end of the rocker arm. The apply force is multiplied to about 5 times its value, then applied to the free end of the band. The band contracts and wraps itself firmly around the planet carrier drum to lock the planet carrier to the casing. An adjusting screw threaded in the casing provides the anchorage point, so the band can be easily adjusted when necessary to compensate for wear. The front servo is a pressure apply, pressure release type with unequal piston areas. It is engaged with the front clutch to provide second gear and acts on a lined spring steel band to lock the secondary sun gear to the casing. The apply force from the piston is transferred through its central stem and multiplied by the rocker arm with its leverage ratio approximately 3:1. This applies the band firmly when second gear is engaged. The apply fluid acts on the smaller piston area surrounding the hollow portion, which accommodates the return spring. If road speed is reduced, the 1-2 shift valve will move to the first gear position. This apply fluid will be exhausted at the 1-2 shift valve, letting the spring return the band to the off position. If road speed increases, the transmission will eventually upshift to third gear. This requires the rear clutch to engage, together with the already engaged front clutch. The front band must be released, but the apply fluid is not exhausted to provide this change. The apply fluid is retained. Then, when the 2-3 shift valve moves to supply fluid to the rear clutch, the same fluid is supplied to the release side of the front servo. Equal line pressures act on each side of the front servo piston, so the larger area on the release side generates greater force. This moves the piston to the released position. If the accelerator is depressed for kickdown or road speed drops off, retaining the apply fluid can provide a snap band application to re-engage second gear. Clutches in automatic transmissions control gear train members. This transmission has 3 clutches. A one-way or overrunning clutch is between the planet carrier and the center support. A multi-plate clutch is inside the drum attached to the input shaft, the front clutch. A multi-plate clutch is inside the drum attached to the secondary sun gear, the rear clutch. The one-way clutch is a sprag type. It locks the planet carrier to the center support whenever the carrier tends to turn in the opposite direction to the transmission input shaft. The inner race of the clutch is provided by an extension on the center support. The outer race is formed in the planet carrier. The equally spaced sprags are held together by a spring-loaded cage. It maintains them in the correct position and attitude. Correct fitting is essential, otherwise the planet carrier will freewheel when it should be locked up, and no drive will be transmitted in D-range first gear. With the sprags in place, the cage moves them so that they share the load equally when the planet carrier is locked. Turning the planet carrier in the opposite direction to the input shaft pivots the sprags towards the larger radius and wedges them between the 2 races. The front clutch is a multi-plate type, engaged in all forward ratios. The clutch operating piston moves in a short cylinder in the clutch drum. A diaphragm-type spring contacts a fulcrum ring on the piston at its inner circumference. Its outer edge rests against a step in the drum. A pressure plate is installed first in the clutch pack so that its fulcrum ring also contacts the diaphragm. When fluid at line pressure is admitted to the clutch cylinder, the piston apply force is multiplied by the leverage provided by the diaphragm. This exerts a greater apply force on the clutch pack than the piston alone could provide, and ensures the clutch is firmly engaged. The spring returns the piston to the off position when the fluid is dumped. Two sets of plates make up the clutch pack: the driving plates and driven plates. The outer driving plates are flat. External splines locate in mating splines in the clutch drum. The inner driven plates have friction material bonded to them. Their splines mate with splines on the outside of a central hub, which is itself splined to the primary sun gear. The friction material can be treated fibre or reinforced paper. It may have a grooved surface to assist in wiping oil from between the plates when the clutch engages. The plates are loaded into the clutch drum against the pressure plate and are placed alternately to make up the pack. The central hub is installed to engage the inner plates and the thrust washer placed in position. The large face of the input shaft acts as the final plate in the pack. The splines at its outer edge transmit the input torque to the clutch drum and the driving plates. The input shaft is retained in the drum by a large diameter snap ring. The number of plates installed determines the torque capacity of the clutch. Installing more plates increases torque capacity, but the clutch must always maintain its set clearance so the plates can separate from one another while in the released position. A centrifugal relief valve in the clutch piston releases fluid trapped in the cylinder when the clutch is released. This prevents partial application of the clutch due to centrifugal force acting on the fluid at high speed. The rear clutch is similar in construction to the front clutch, but with a larger diameter piston and a coil-type return spring. This spring is compressed against the face of the clutch piston when fitted. The outer plates in this clutch are the driven plates and are splined to engage with the splines in the clutch drum as before. These plates may have a flat surface or a slightly dished or coned surface. The dished plates provide a cushioning effect, which assists with smooth engagement when the clutch is applied. The plates may be fitted as a pack, with the dishing in either direction, but all of the dishing must face the same way, or clearance may be compromised. The inner plates are splined to mate with splines on an extension on the front clutch drum. They transmit the drive from the input shaft to the outer plates when the clutch is engaged. The clutch plates are assembled in the pack alternately, with the steel plate placed first against the clutch piston. The pressure plate is assembled last, and the pack is retained in the drum by a snap ring. The hydraulic system has a crescent-type gear pump, a centrifugally operated hydraulic governor, and a control valve body assembly to regulate the pressure and direct fluid to the appropriate components. The pump is driven by tangs on the converter spout and operates whenever the engine is running. It supplies all the hydraulic requirements of the transmission during operation. The governor is driven by the transmission output shaft and provides a hydraulic pressure that varies with vehicle speed. This variable pressure is used by the valve body as one of the inputs to control upshifts and downshifts. The valve body has all the valves needed to control the transmission at all stages of operation. They are mostly spool-type valves, but disc and ball check valves are also used. Cylindrical spool valves have a number of distinguishing features. The lands are the raised portions of the valve, while the reduced diameter between each pair of lands is referred to as a valley. The face of each land is square and sharp to the land diameter. Some valves have a stem or extension on one end to locate a regulating or return spring or to limit valve travel. Sharp corners on lands keep out dirt particles and give the valve a self-cleaning action as it moves back and forth in the bore. There is only small clearance between lands and the bore for each valve, so they must be handled with care. Spool valves can be positioned manually, or by springs, or by pressure, and in many applications have lands of different diameters. In this case, the different diameters result in a larger face area on land 1 than on land 2. This is known as a differential area. When fluid under pressure enters port B, this differential area creates a differential force. This moves the valve to the left since the force acting on land 1 is greater than the force on land 2. Alternatively, the valve could be moved by admitting fluid at port C. In both cases, the valve movement allows previously blocked fluid at D to flow between lands 3 and 4. It exhausts at E or passes to some other part of the system. If fluid pressure is removed from C, the valve remains stationary. Even if fluid is admitted at port A, no movement can occur as the areas on lands 2 and 3 are equal and both generate an equal force. The valve can only be moved back to its original position by introducing spring pressure or fluid pressure on the left-hand side of land 1. The valves can be divided into two groups: pressure regulating valves and those that direct flow and pressure, or flow control valves. Spool-type valves are suitable for pressure regulation in automatic transmissions, as variable pressures are needed. In this regulating valve, the valve spring is compressed when pump or supply pressure is high enough. The larger land then uncovers an exhaust port to maintain a regulated output pressure. Similarly, with this regulating valve in a fluid circuit, the valve is forced downwards against its spring until it uncovers a port to another part of the circuit. Since the port is not fully uncovered, flow is restricted, which causes a pressure drop across it. Fluid pressure in this part of the circuit falls below that of the fluid being supplied. Once the port is fully uncovered, pressures on both sides of the valve become equal. Control valves are simple gate-type valves, which open or close off a circuit without altering pressure. The manual valve connected to the gear lever is a control valve, which directs fluid to components when a drive range is selected. Control valves can also react to changes in pressure. This shift valve is held at the end of its bore by spring tension. It blocks the fluid under pressure at port A. The larger differential area at port C is subject to governor pressure. As road speed rises, the rising pressure forces the valve to the left, and fluid flows across from port A to port B. This can be directed to operate the next clutch or servo and change the transmission to a higher ratio. As road speed falls and governor pressure diminishes, the spring moves the valve back to cut off the fluid supply and the transmission downshifts. Orifices are often used in conjunction with spool valves to restrict fluid flow for timing purposes or to prevent valve fluctuations. The orifice is designed to prevent sudden or undue movement of a valve. In this basic primary regulator valve, the orifice is in the circuit leading to the large differential spool area. The buildup of line pressure from the pump acts via the orifice to move the valve against the spring force. This uncovers the exhaust port to release excess fluid and allows fluid at a controlled line pressure to pass to the rest of the hydraulic system. The pressure is determined by the tension of the spring. However, pressure fluctuations are reduced because the orifice prevents the valve from reacting quickly and thus stabilizes the regulated pressure. The hydraulic system of this transmission has a number of regulating and control valves. They can be identified in this hydraulic circuit diagram. This valve controls fluid pump output to maintain the required line pressure in the system. Line pressure is the highest pressure in the transmission. All other pressures are derived from it. This valve reduces line pressure to a low value for use in the torque converter and in the cooler and the lubrication circuits. This valve is positioned manually by the driver operating the selector lever. It's a control valve which directs line pressure in and out of circuits when each range is selected. This valve shares a common bore with the downshift or kickdown valve. Both are influenced by the downshift cam, connected by a Bowden cable to the accelerator linkage. The throttle valve re-regulates line pressure to a value which is proportional to throttle opening. The resultant throttle valve or TV pressure varies from 0 at closed throttle to line pressure at full throttle. This pressure is supplied to the spring end of the shift valves to delay upshifts relative to throttle opening. The wider the throttle opening, the greater the TV pressure and the higher the road speed will be before an upshift will occur. TV pressure is also directed to the spring end of the primary regulating valve. As the accelerator is depressed, it progressively raises line pressure. This ensures the engaged servos or clutches are securely applied when high torque is being transmitted and allows the pump to operate at lower pressures at other times. This reduces pumping losses and lowers fuel consumption. The 1-2 and 2-3 shift valves are control valves, which are supplied with line pressure from the manual valve. They either block fluid or allow it to flow at prevailing line pressure to a clutch or band. Their operation is determined by a spring plus TV pressure at one end. This acts in opposition to governor pressure at the other end. This valve is mounted on the transmission output shaft and rotates with it. It re-regulates line pressure supplied from the manual valve in relation to vehicle speed. When vehicle speed is low, governor pressure is low. When vehicle speed is high, governor pressure is high. Governor pressure is directed to the end of the shift valve to oppose TV and spring pressure. This produces upshifts relative to vehicle speed. This valve is included in the throttle valve combination. When the accelerator is depressed fully, the downshift valve supplies line pressure onto the spring end of the shift valve. If road speed is below a certain value, this forces the shift valve to move and initiate a downshift to a lower gear. This valve is in the circuit to the release side of the front band servo. It is a timing device. When a 2-3 upshift is made at higher road speeds, it correlates front band release and rear clutch application. Conversely, it correlates rear clutch release and front band reapplication when a 3-2 downshift is made under similar conditions. This valve makes line pressure and throttle pressure sensitive to road speed. At higher speeds, it cuts back these pressures to allow smooth upshifts. It also moderates line pressure increases produced by wide throttle openings during stall or upshift conditions. High throttle pressures produced at these times raise line pressure very high. This is because the throttle pressure is applied to the spring end of the primary regulating valve. Modulator pressure is applied to the opposite end of the regulating valve to counteract this and moderate its influence. This is a summary of the basic action of the valves in the hydraulic system. The primary regulating valve maintains line pressure in the system. Line pressure is directed to the manual valve and to the throttle valve at all times. The secondary regulating valve determines the pressure in the converter and in the lubricating circuits. The manual valve directs line pressure to the shift valves and to the governor valve. The shift valves direct line pressure to the band and clutch servos. Governor pressure is directed to one end of the shift valves, while throttle valve pressure is directed to the other end. Throttle pressure is also directed to the spring end of the primary regulating valve to boost line pressure as required. The valves act together in the system, but their operation can be considered separately. The primary regulating valve has a number of lands, including one larger land which provides a differential area. A central stem locates the regulating spring. Fluid from the pump can act on the valve through a 1 mm diameter orifice in the circuit. With the valve at rest, the two central lands block the flow of fluid across their valleys. The spring end of the valve is subject to throttle pressure through a circuit connection from the throttle valve. The lower end is subject to modulator pressure acting on the lower face of the bottom land. A vent between the two uppermost lands prevents hydraulic lockups due to fluid seeping into the valley between them. In operation, fluid from the pump enters the valve through the orifice and acts against the differential area. As pressure rises, the valve moves upwards against its spring. Excess fluid can then pass across the two large valleys to the ports in line with them. The result is an initial regulation of line pressure at idling speed. This line pressure is directed to the manual valve and the throttle valve at all times. When D is selected, line pressure is also directed to the front clutch, to the 1-2 shift valve, and to the governor. Excess fluid passing across the valleys is directed to the secondary regulating valve and the converter. Fluid from the lower port of the primary regulator valve acts on the end face of the secondary regulating valve. This raises it against its spring. Valve movement uncovers a port to the lubrication circuit for the rear end of the gear train, and then an exhaust port leading back to the pump inlet. The exhaust bleed-off stabilizes fluid pressure in the lubrication and converter circuits within acceptable limits, from 100 to 200 kilopascals. Line pressure needs to vary in step with accelerator position and vehicle speed. That requires extra control over the primary regulating valve. High line pressure will hold a band or apply a clutch securely to prevent slippage when the accelerator is depressed and high torque is transmitted. Once the vehicle is moving and the transmission is upshifting, less torque is transmitted, so lower line pressure is adequate. Applying throttle pressure to the spring end of the primary regulating valve lifts line pressure. Applying modulator pressure to the opposite end reduces it. Line pressure is supplied to the throttle valve at all times, and throttle pressure is derived from it. At closed throttle, the throttle valve is at rest and line pressure is blocked off by a land. Throttle pressure is zero. Depressing the accelerator transfers movement through the kickdown valve and spring. This opens the throttle valve and the land uncovers the line pressure port. Fluid at line pressure is now metered into the throttle valve circuits and a TV pressure is quickly established. It extends through the orifice to the valve reaction area. This tends to close the valve against the spring force, minimizing pressure fluctuations. A balance is established to produce a TV pressure relative to the accelerator position. TV pressure can vary from 0 to around 1200 kilopascals. TV pressure is directed back through the circuits to the spring end of the primary regulator valve. It helps the spring oppose the force of fluid acting on the valve's differential area via the orifice. TV pressure holds the primary regulator valve down to increase line pressure according to throttle opening. This ensures clutch and band apply forces are maintained in step with throttle position. Once a vehicle is moving, the primary regulator valve needs to reduce line pressure to assist smooth gear shifting and fuel economy. Modulator valve pressure is directed to the end of the valve opposite to the regulating spring. The modulator valve assembly is in two sections: a modulator valve and a modulator plug and spring. The modulator valve operates by throttle pressure, but is also subject to governor pressure, so its output responds to accelerator position and vehicle speed. Throttle pressure directed to the modulator valve moves the valve up and forces the plug down against the compression of the spring. Separating the valve from the plug re-regulates the throttle pressure to modulator pressure. It is then directed to the end of the primary regulator valve opposite the spring. If the accelerator is fully depressed, high modulator pressure forces the primary regulator valve upward to oppose throttle pressure and spring pressure. This prevents excessive line pressure under stall conditions. Rising vehicle speed develops governor pressure, which is directed onto the large land area at the end of the modulator valve. When governor pressure overcomes throttle pressure, it forces the modulator valve down. That forces the modulator plug to bottom out. The modulator plug can then no longer reduce the incoming throttle pressure. Undiminished throttle pressure will now exist in the modulator circuit. The regulator valve is forced up, reducing line pressure for a smooth upshift. This reduction in line pressure is called the cutback point. Moving the modulator valve down allows throttle pressure to pass between the modulator valve lands. This passes into a circuit, returning to the smallest reaction area at the end of the throttle valve. This pressure acting through the orifice in the circuit helps move the throttle valve to the left against its regulating spring. This reduces the initial throttle valve pressure established in the throttle pressure circuit, and in turn further reduces line pressure. When D range is selected, the manual valve directs fluid at line pressure to the front clutch, which remains applied in all forward gears. Fluid is also directed to the governor and the 1-2 shift valve, where it is blocked at a differential area. A separate circuit from the manual valve directs line pressure to a differential area of the 2-3 shift valve. This is held in the downshifted or 2 position by a combination of the differential force and the spring force. The 1-2 shift valve is in 2 sections. The shift valve itself is the lower section, held in its downmost position by a combination of the differential force and the upper section plunger and spring. As soon as the accelerator is depressed, throttle pressure helps hold the valves in the downshifted position so that their movement is influenced by accelerator position. When the vehicle is moving, the governor re-regulates line pressure supplied to it and directs this pressure to the large land areas at the bottom end of the shift valves, to the servo orifice control valve, and to the modulator valve. The governor is in 2 sections: the valve and its spring, and a central stem and bob weight retained by a C-clip. It operates by centrifugal force in 2 stages. In the first stage, at lower road speeds, the bob weight and valve act as one unit. Rotation of the governor throws out the bob weight, causing the valve to uncover the line pressure supply port, and fluid under pressure flows through the port to exert thrust on the face of the valve. This thrust increases until it can close the valve against the opposition of the centrifugal force. The valve action produces a pressure at the outlet proportional to the force acting on the bob weight. As speed increases, pressure needed to close the valve increases also. For any given value of line pressure, the result is a governor pressure which increases with speed. The second stage starts when the bob weight stop contacts the body. Balance between opening and closing the valve is now achieved by the centrifugal effect on the valve and the fluid acting on its pressure face. Governor pressure acts on the end of the 1-2 shift valve. As road speed increases, it becomes high enough to overcome the opposing spring and throttle pressure. The shift valve assembly moves upward and lets line pressure pass into the circuit to the apply side of the front band servo. The transmission is now in second gear. Once the 1-2 upshift occurs, the differential area is no longer effective. Governor pressure must fall to a lower value to let the valve return to the first gear position, so a 2-1 downshift cannot occur at the same road speed as the upshift. Downshifts occur only at vehicle speeds below those at which upshifts occur. This shift spread prevents a transmission hunting up and down between ratios. It is called shift speed hysteresis. Additional force can be provided to produce a 2-1 downshift under kickdown conditions. This is provided by the kickdown portion of the kickdown throttle valve combination. When the accelerator is fully depressed, the kickdown valve closes off the exhaust from the kickdown circuit and forces the throttle valve to the end of its bore. The throttle valve can then no longer regulate the incoming line pressure. Throttle pressure now becomes equal to line pressure and passes into the kickdown circuit, leading to the kickdown port at the 1-2 shift valve. Fluid passes across the valley area and onto the spring end of the plunger. The force this provides overcomes governor pressure and returns the shift valve to the first gear position. This releases the front band by opening its apply circuit and exhausting the apply fluid back to the pan. As road speed rises, governor pressure increases. It acts on the large differential area on the bottom land, so governor pressure will become high enough to force the valve upward and overcome kickdown pressure. This keeps engine RPM within safe limits in the automatic range. When 1 is selected, the manual valve supplies line pressure onto the differential area and through a separate circuit to apply the rear band. The application of the rear band provides engine braking on overrun. This circuit passes through the bottom valley area of the valve and acts on the large bottom land to hydraulically lock the shift valve down. Governor pressure cannot force an upshift, so the transmission will remain in first gear until the lever is moved to 2 or to D when an upshift can occur. Once the transmission upshifts into second gear, the rear band circuit can exhaust at the shift valve. The rear band is inoperative in first gear when D is selected, as its circuit is open to exhaust at the manual valve. Choosing position 2 directs line pressure to the front clutch, the governor and the 1-2 shift valve. The vehicle will move off in first gear and change up to second gear as soon as governor pressure is high enough to move the shift valve up and let fluid pass to the apply side of the front servo. No further upshifts can take place since no line pressure is supplied to the 2-3 shift valve. The valve moves upward under governor pressure, but it controls no fluid flow and no changes can occur. The 2-3 shift valve assembly consists of the shift valve, its spring, and a throttle pressure regulating plug. In D range in second gear, line pressure from the manual valve is applied onto a differential area. This helps the spring hold the valve down against governor pressure. In this position, the rear clutch apply and front band release circuit is open to exhaust. With the vehicle moving in second gear and a minimum throttle opening, throttle pressure applies to the top of the regulating plug. But then, throttle pressure is too low to move the regulating plug downwards. The only forces opposing governor pressure are the spring and the line pressure on the differential area land. A 2-3 upshift occurs at relatively low vehicle speed. With the vehicle in second gear, at higher throttle openings, higher throttle pressure moves the plug down towards the shift valve. This re-regulates the throttle pressure to a lower value so that it can act on the top land of the shift valve. This helps the spring control the shift points relative to accelerator position at lower vehicle speeds. As soon as governor pressure is high enough to overcome the opposing forces, the valve upshifts into top gear position. Fluid at line pressure flows across to apply the rear clutch. At the same time, fluid passes through the servo orifice control valve to the release side of the front band servo. The front and rear clutch are the only components being applied, so top gear is achieved. The servo orifice control valve is a timing device. It prevents engine flare at wide throttle openings on a 2-3 upshift. It also stops transmission tie-up, that is, being momentarily in 2 gears during a 3-2 downshift. It's a shuttle valve, which can be held at rest by a spring to allow unrestricted fluid flow. Or it can be moved by governor pressure to insert a restricting orifice in the front band servo release circuit. At low vehicle speeds, governor pressure is not high enough to move the valve. When the 2-3 upshift occurs, fluid flows unrestricted to the release side of the front servo. This type of shift occurs at light throttle openings, so the rapid clutch and band actuation does not cause engine flare. At wider throttle openings, vehicle speeds are higher before an upshift occurs. So governor pressure will have built up enough to move the valve, so fluid must now pass through the orifice. This slows the release at the front band and ensures the rear clutch is fully applied and able to transmit torque as the band comes off. This prevents engine flare. On a downshift at high vehicle speeds, the orifice slows the release of fluid from the release side of the front servo and therefore the reapplication of the front band. Then the rear clutch comes off as the band is applied, preventing a lockup in the transmission. When a 3-2 kickdown downshift is required, the fully depressed throttle stops the throttle valve regulating the incoming line pressure. Throttle pressure becomes equal to line pressure. Fluid at line pressure passes through the kickdown valve and acts on the top land of the 2-3 shift valve. If road speed and governor pressure are low enough, the force provided will move the valve down and effect a change to second gear. Then if road speed rises enough, governor pressure will overcome the opposing forces and move the shift valve upwards. If road speed is above a certain minimum, a downshift is denied, preventing over-revving.